Hello everyone and welcome to the TLE Eliminators PCD for Codeforces Round 1055, Div 1 plus Div 2. Today we'll be discussing the problems from A to D. Okay, system testing is going on. So, how was the contest, guys? How was the contest? How many questions did you all solve? Hi, MacDon. Hmm, I guess less viewers today. I suppose it's late. Is that why? Anyways, no matter. So we'll be discussing the problems A to D one by one, right? And before we get started, if you haven't checked it out already, go check out teliminators.com/courses. Here we have more than 4 different levels of courses, each corresponding to a different stage in your competitive programming journey. So they start from level 1, which is all the way in the basics, basic maths, time complexity, sorting and searching, all the way to level 4 for people who can solve 3 problems in CF-Div2, and they need to brush up on stuff like dynamic programming, graphs, disjoint set union, etc. Right? Each course has more than 40 hours of recorded lectures, more than 100 practice problems, hints and video solutions for the problems, as well as doubt support, as well as progress tracking. So you're always motivated, right? So do definitely check out the Telemeters course. I think it's at super affordable prices, right? So yeah, go check it out. Could only solve A. Yeah, I get maybe B was a bit tricky. Yes. B was a bit tricky. Yes. Although C was, to be honest, easier. Like B and C have been given the same number of points. And to be honest, I found that C was the easier one. So you should have tried C as well. But anyways, yeah, let's get right into the solutions. So problem A, increase or smash. I can't pronounce that name, so I will not attempt to. But there is an array A consisting of n zeros, and you have to transform it to some target array which is given to you. So there's an array of A, n zeros, and you must transform it to target array. And one operation is choose X and add all elements with X, and the other operation is convert all elements of convert some elements to 0. Okay, so the first operation is add all elements with X, and the second element is convert some elements to 0. uh, each is one operation. What is the minimum number of operations required to get our target array? N goes up to 100, so yeah, n square n cube solutions will also pass, right? Yeah. Okay, so let's think about it. All right, so we are given basically an array which starts as all zeros, right? An array which starts as all zeros, and then um, we need to convert it to some target array. Like in the first example, it's 113, right? So we need to convert it to 113. So how do we do that? What if we add everything with 1? Okay, what if we add everything with 1? Now it looks like this, but we cannot selectively add 2, right? We cannot select a single element and add 2, right? And add 2. Cannot select a single element and add 2. So what this means is that in order to add this 2, what we should have done was, instead of doing this, right, this is wrong. Instead of doing this kind of sequence of operations, what we should have done was, first itself, we should have added that 2, right? At the very beginning, we should have added that 2, right? Then we can smash the 2 from these two, right? We can smash the 2 from these two, right? And we get to this 0, 0, 2. And now we can add 1 to all elements, right? Now if we add 1 to all elements, we get our target array, right? So basically what we saw was, we cannot obviously select a single element, right? We cannot do this. We cannot select a single element and add 2 because the addition operation runs on all the elements, right? So basically what we're doing here is that instead of doing that, we will add the 2 initially itself to all the elements. Then after that, we will smash the remaining elements, and then we will add back this value, right? We'll add back this value. So what observations can we make here, right? Obviously, we can do other examples, but if you do some other examples, you'll make the following observation. So the observation is that um, basically, if you have created like all values equal or less than equal to some value, and you want to create a larger value, then the larger value is the limiting factor. Okay, so the larger value is the limiting factor. Like basically, here in the example we had 113, right? So when we create 111, we are getting limited by the fact that we're not able to make a 3 by adding a 2, right? So basically, the larger value is the limiting factor. So whatever this larger value is, like 3 is equal to 1 plus 2, right? 3 is equal to 1 plus 2. So basically, what we need to do is we need to make this 2 first, then this 1, right? So what if we had more elements? What if we had more elements? Um, let's say we had the elements like 1, 2, 3, 4, 5, right? And what would we do in this case, right? What would we do in this case? Um, let's say all the elements were 0 in the start, right? All the elements in the array were 0. Then now, what is our limiting factor? 5, right? So what we're going to do is we're going to add 1 to everything, because as you can see, 5 is equal to 4 plus 1, right? So 5 is equal to 4 plus 1. So what we'll do is we'll add 1 to everything, right? Because if we won't be able to create numbers larger than 4, right? So we're going to start by adding 1 to everything. So we get all ones, right? Then after that, we will wipe some of these into 0, right? And leave the last one as 1. Then again, we will do this process. We'll add ones again. So it will become like this: 1, 1, 1, 1, 2. Then wipe zeros, and it will become 0, 0, 0, 1, 2, right? And so on. If we keep repeating this process, we will get our target, and our target will be 1, 2, 3, 4, 5, right? So basically, the larger numbers, whatever quantity is there, we are adding it beforehand, right? So this brings us to our second observation. Observation 2. So for the largest number, essentially we are doing uh, essentially we are doing one operation, right? If you count them up, we are doing one operation for that largest number, which is the initial one, right? And for every other number, for every other number, we are having to do two operations. Okay, we are having to do two operations, like essentially, because what we are doing is um like when it's initially all zeros, right? It was initially all zeros, and then let's say the largest number was 5. So to fix 5, we added 1 everywhere, right? So we added 1. Now this does not need to be touched, right? This does not need to be touched, but here two operations are being taken, right? Here two operations will be taken, because first we have to erase. First we'll have to erase, and then we'll have to um, continue adding, right? So basically, if you are given the number of distinct numbers, right? If you're given uh, if the input if the input had n distinct numbers, right? If the input had n distinct numbers, our answer will be our answer will be 2 times n minus 1, right? Because the largest one only takes 1, all the others take two operations in essence. So basically, let's say for example, our numbers are 1, 5, and 7, right? So we can write this as 1, 1 plus 4, 1 plus 4 plus um, 1 plus 4 plus 2, right? So this is what this will break it down, like we're basically breaking the number down. So I hope you understand. We're breaking these numbers down, these numbers down, right? So first we have to add 2, which is the contribution for the largest element. Then we'll have to erase 2, right? So add 2 and erase 2 on these two basically. Then we'll have to add 4, right? And erase 4. And then finally we'll have to add 1, right? So basically what happens is for each of these we are adding and erasing, but for the last one we're not erasing, right? So here we're adding and erasing this, right? So add and erase is happening in these, and for the last one only add is happening, right? So that's why the answer is 2n plus 1, 2n minus 1. So I hope that's clear. So let's look at implementation. The way I implemented it was I took it in a set because I want only unique numbers, right? And then you can use hash map as well because it's only up to 100, or you can use arrays as well. But yeah, I took it in a set, and then I printed 2 times the size of the set minus 1, right? 2 times the size of the set minus 1. Time complexity, you can make it big O of n if you want, but here the time complexity is big O of n log n because we use sets, right? But since n is only 100, doesn't really matter either way. Yeah. Yeah. So obviously you can backtrack from the final array to the answer of zeros. Yeah, that's a pretty nice way to do it. Okay, so everyone clear with problem A? Basically, the essential idea of problem A is that we are breaking down each number, especially the larger numbers, into like a sum of the differences from smaller numbers, right? So 5 is broken down as 1 plus 4, 7 is broken down as 1 plus 4 plus 2, and then first 2 will be added, then 2 will be erased for the others, then 4 will be added, 4 will be erased for the others, 1 will be added, but it does not need to be erased. So that's why the answer is 2n plus 1, right? Does that make sense? Put yes, no, guys, if that explanation is understanding. And we'll move on to the next problem. I think problem B did trouble a lot of people today. So yeah, that's going to be the interesting problem to discuss. Right. Okay. So let's move on to problem B. Okay. Catching the Krug. So basically what is going on in this problem? We have a grid numbered from 0 to n, right? So total n plus 1 into n plus 1 cells. And there is a Krug and there is a Doran or something. And basically the Krug can move up, down, left, right. So it can move vertically or horizontally, but not diagonally. And Doran can move up, down, left, right, diagonal also. So Krug is like just normal up, down, left, right, and Doran is like a king in chess basically. So you can move all these 1, 2, 3, 4, 5, 6, 7, 8 directions, right? And they can also stay at the same cell as well. So they can either move or stay at the same place. That's both valid, right? And basically the Krug is trying to escape from Doran, and Doran is trying to catch Krug basically. The Krug's survival time is the number of turns uh, that the Krug can escape, like the Krug can stay away from Doran, assuming optimal play, right? Assuming optimal play. And for each test case, we need to output the survival time. If he can survive for infinite turns, output -1. Now, as you can see, n goes up to 10 to the power 9, and all the coordinates also go up to 10 power 9. So basically, obviously, we can't do big O of n solution, right? We need to, or even n squared for the grid. We have to have some like easy log n or big O of 1 strategy to find the answer for this. And mostly it's going to be mathematical or something like that, right? So how do we go about of this? How do we go about this? So let's just visualize the problem, right? So let's make a grid, okay? And here's our Doran. So let's mark it as D, right? And at this position, right? So this is his X and Y coordinate, right? And there is a Krug, let's say somewhere here. Okay, and imagine that this is a grid. You have to imagine that this is a grid. Fine. Okay. So how do we go about this, right? So one thing we can think of, so if you play some chess, The Doran is basically a king, right? So one thing we can think of is like if you make um like this is the vertical line which Doran is on, and this is the horizontal line which Doran is on. So basically they are like four different regions which are there, right? And the Krug is in one of them. Now basically what is happening is Doran he can move like this, like this, like this, right? And he can always ensure that wherever the Krug is going, he will always move this thing closer or this thing closer to him, right? So this line or this line will always go closer to the Krug. So this Krug, he can let's say try to run this way, and Doran will also run this way, and then let's say Krug runs this way. Doran will also come after him, right? So basically that is what is happening. Similarly, if Krug tries to run this way, Doran will try and run this way, right? So it's like a box. This thing is basically forming a box around the Krug, right? And he's trying to enclose this box slowly. And as you can see, since the board is finite, right? The board is finite. Um, from this idea that we have a box formed like this, and at each step, the box will simply become smaller. Either it will become smaller this way, or it will become smaller this way. You can prove that this will always happen, right? Um, we can show that Doran will always be able to catch Krug. Okay, so Doran will always catch Krug after some time. So minus one case is impossible. Okay, minus one case is impossible. Okay, so yeah, even if you look at the test cases, they never gave a minus one test case, which is obviously very suspicious, right? That should already put it into your mind that minus one case might not be possible, right? So what is the next thing? Okay, what is the next thing? So obviously you can do solve this with intuition and stuff because it's a very ad hoc and almost like IQ testing type of problem. But there is a systematic way to also do this, right? There's a systematic way to also do this. And the thing is, we need to consider what is known as relative position. Okay, so what is known as relative position? All right. So we need to focus on the relative position. What is relative position? So let's say this one is x2, right? Or actually Krug is x1, right? Okay. And Doran is x2. Fine. So let's say this is x1 and x2. Now this difference which is there, right? This difference, we'll call this delta x, right? So this is the relative position between D and K, right? And similarly, we will call this position over here, right? So this is y1 and this is y2. So this difference which is being formed, this will call as delta y, okay, delta y, and we'll call this as delta x. Fine. So everyone clear with what relative position is, right? I think that everyone would know. What if K goes downward, escaping the box? Yeah, that's fine. But the thing is, either the box closes on him from one side or from the other side, right? So even if he goes downwards, we can move one step ahead, so the box still gets smaller itself. So this is to answer MacDon and Red both. Even if he goes down, if we go one step to the right, the box will become smaller by one dimension. So basically, I was just Doran will always crack because no matter what, box will always get smaller. That's what I'm trying to say. The box gets smaller at each he moves down. And anyways, there's some limit to where he can move down, right? It's a finite board. So yeah, that's the point. Anyways, so let's go back to our thoughts. We were thinking about relative position, right? So we can draw that in space as well now. We can remove the box. So let this be Doran and Krug. And this is your delta x. This is your delta y, right? So now observe how Drug and whatever Doran and Krug, sorry, how Doran and Krug can affect the values of delta x and delta y. Okay, how do how do the moves how do the moves affect delta x and delta y, right? So this is what we're going to figure out. Okay, so we're going to think about these two quantities and we're going to figure out how it affects. So now, um, yeah. So now who moves first? Krug moves first, right? So it starts from Krug. Now what can Krug do? Let's think about what can Krug do. Okay, so Krug has um so there are two quantities delta x and delta y, right? So what Krug can do is he can move either up, down, left, right. Yes. So one thing he can do is if there is enough boundary, right? If he's not at the boundary, if he's still somewhere in the middle itself, he can do delta x plus one, right? He can do delta x plus one, delta y, right? Or he can do delta x remains as it is, and he can do delta y plus one, right? So he can basically do this, right? So he can change the value of delta x to delta x plus one by moving basically one step away in this direction, right? If he moves one step away in this direction, it becomes delta x plus one, right? Or if he moves one step away in this direction, it becomes delta y plus one, right? So that's what he's changing in these two quantities, right? He can make it delta x plus one or delta y plus one. Now, what about Doran, right? What about Doran? So now, what can Doran do? Doran can he can change both the quantity as one at once because he's moving diagonally, right? He's moving diagonally. So, for example, if you have delta x and delta y, then what he can do is he can convert this to um, delta x minus one, right? Because he wants to move closer. So minus one basically means if Doran went from here to here, right? So now this new value is delta x minus one, right? This new value is delta x minus one, right? Similarly, if Doran went from here to here, so he went diagonally, then this would become delta x minus one, delta y minus one, right? Think about it. This would become delta x minus one, delta y minus one, right? So in one step, Doran can make it delta x minus one as well as delta y minus one, right? And it is obviously beneficial for him to decrease the value of delta x as well as decrease the value of delta y at the same time. So he's moving closer in both the dimensions, right? So observe that this is Krug, right? So Krug can move away from him in one dimension, right? X and Y are the two dimensions or two coordinates. So Krug can move away, can move away along one coordinate, along one coordinate. Meanwhile, Doran can come closer in two coordinates, right? Doran can come closer in two coordinates, right? Now, obviously, if this was an infinite board, he could keep moving away forever. But obviously, Krug cannot move away forever. So, what is the distance he can move away? That also we'll see, right? We'll see what is the distance he can move away. So, let's say here is Doran, and here is Krug, right? So, this is their delta x, delta y, right? So, in the y direction, he can move this thing. We'll call it y dash. Okay, he can move up to this border, which is y dash. In the x direction, he can move up to this border, which we'll call x dash, right? And this is the maximum he can go. After that, he will stop making moves, right? So he can do this until he hits x dash. Similarly, he can make this move until he hits y dash. It's y dash moves. Basically, he can do that many moves, right? So he can reach the border. Until he hits the border, he can make that many moves. Right? So let us try and simulate this game. Okay, so now the game has become much more different. Instead of having geometry, it is like having two piles of stones, right? Instead of becoming a geometry problem, which is complicated, we have transformed it to a problem with two piles of stones. One pile has delta x stones, right? The other pile has delta y stones. Imagine it. Okay, that's their distances. That's their relative distances. So let's say one pile had, let's say, four stones, right? And the other pile had six stones, right? So we're completely transforming the problem, but as you can see, the problem remains equivalent, right? So one pile has four stones. So I didn't draw them very evenly, but just imagine that this is six, right? Now at one step, what is um what is basically Krug doing? So Krug is basically he's able to add one stone to one of these piles, right? He's able to add one stone to one of these piles. Let's say he added this stone, and what is Doran doing? He's removing this stone as well as this stone, right? So he's removing two stones from this pile, right? One from this pile and one from this pile. So as you can see, let's say this gets removed and so on, right? So basically, this is the transform version of the game, right? And this is a very, this seems like a much more familiar game theory problem now, right? Okay, so how would we go about this? Okay, so if you observe, basically in Doran's next step, he will be removing the top two most stones, right? He's going to remove the top two stones. So by what Krug is basically doing is he's going to be adding one stone, right? He's going to be increasing one distance, which will get removed in the next turn. But basically, he's choosing one distance to preserve, right? So if your distances are 4, 6 in delta x, delta y, then it becomes, let's say he makes it 5, 6, then it will become 4, 5, right? So he's, since Krug added one distance over here, Krug moved one distance over here, he's adding one, which is getting subtracted, both of them are getting subtracted, right? So this is the process which is happening. So now people who did not get this problem, you can try and you can think about it, right? If you want, you can pause the video and you can think about it from this logic, right? Of two piles of stones, which is equal to the relative distance delta x, delta y. Maybe you'll get it. Obviously, we'll get into the solution from this point onward, right? So this is the transformation of the problem we have done so far. Okay. So now one very important thing, obviously, is the limiting factor, right? So we said y dash and x dash is the maximum amount which a given quantity can go, right? So um, basically, when we have x dash and y, delta x and delta y, at each step, if you count both Krug's and Doran's steps, so Krug does a step and Doran does a step, then essentially it's either becoming delta x minus 1 comma delta y, or it's becoming delta x delta y minus 1, right? If we count both their steps together, right? So Krug moved one forward and Doran moved minus 1 on both the sides. So that's why it's becoming one of these two, right? One of these two, correct? And this continues for some time, right? This will continue for some time, and it can become like in another step, this can become something like delta x minus 2 comma delta y, or it can become um, delta x minus 1, delta y minus 1, right? Or this can become, this can also go to the same position basically, right? And it can become delta x, delta y minus 2, right? And this basically continues on until there comes the point where um, he has used some y operations here, right? Y dash. He has gone closer to the border. So he'll stop be able to preserve this value of y, right? Krug will stop being able to preserve this value of y, and then both x and y will start decreasing after that. After that, both x and y will start decreasing, right? Because he has reached a boundary basically. He has reached a boundary. That's basically what has happened. So what this tells us is that um, if he, let's say, tries to go away from the x coordinate, right? If he tries to go away from the x coordinate, then he can survive up to delta x plus that x dash, right? He can survive up to the delta x plus this x dash amount, right? So that much time it will take for Duran to catch up with him, right? Because x dash times it will not even change, and then delta x time will be taken to catch up to him. Or if he tries to defend only the y direction, then it will take delta y plus y dash, right? It will take delta y plus y dash. We can show that if you take max of these two, right? If you take max of these two, that is our answer. Okay, that is our answer. Or in visual terms, what it means is the maximum distance to boundary, right? So if we have um like this is our k, right? So the whatever the maximum distance to the boundary is, so from here to this boundary, so this is boundary one, right? Delta x plus x dash, and this is boundary two, so delta y plus y dash, This is the maximum distance, which is going to be the answer, maximum of these two, right? The simple reason is because each time we are doing a -1 on one of them and not affecting the other one, as long as he's not on the boundary, right? And once he's on the boundary, both of them will start getting affected. And so it is optimal to defend the coordinate which we can defend for longer, right? So let's say delta y was 5 and y dash was like 10, right? So we can still defend it for 10 more moves. Meanwhile, delta x was, let's say, 6, but x dash was 2, which means we can defend it for 2 more moves. Then it's better to defend this, right? So whenever y dash gets subtracted by 1, we will add 1 to that y dash and make sure that it remains its original value, right? And once we run out of that, and once we have reached the boundary, till then x would already be over. Till then, x would already be over, right? So that's why it's best to defend whichever coordinate gives us the maximum room to the border. Or basically, what we have proved is we have proved that starting from Doran, we are going to move away to the boundary, right? Either this boundary or this boundary. We're going to move to the maximum distance away from Doran. That is going to be our answer, right? So our final conclusion from this game is that conclusion, conclusion, move to the boundary, move to the boundary, which is farthest away from Doran, right? And once we have reached that boundary, basically when Doran is catching up to us, obviously this delta x will become 0 anyways, so there's no point, right? Since it's the farthest boundary. So that means that this delta y was all the plus del y dash is used up. So that means this also would have definitely been used up. So yeah, that's why this is our answer. The logic is right, but yeah. Okay, MacDon. So you're saying that once he reaches the border, he can still preserve one coordinate by moving in a particular direction, right? But what I'm saying is once he reaches the border, once he reaches the border, once he reaches the border, which is max of the two, which is max of delta y plus y dash and delta x plus x dash, right? Then the other coordinate is already caught up with, okay? Then the other coordinate is already equal to 0, okay? The other delta x. Let's say if he was reaching him, let's say if we were going towards the vertical one, okay? Let's say we're going towards the vertical border, then basically we're preserving delta x plus x dash, right? We're preserving delta x plus x dash. In that case, what delta y would have already become 0 by then. Okay, delta y would have already become 0. And I'll show you why that happens. So let's say we have Duran over here, we have Kreg over here, right? And obviously, this is the longer bound border, right? So Kreg should run in this direction, right? So assume that Kreg runs in this direction, one step at a time. He runs towards this direction, right? Kreg runs in this direction. So this is Kreg after some time, he's going like this, right? So what Duran is going to do is he's going to also catch up with him, right? So he's going to go plus one, and Craig is simply going +1 in this direction, right? So the delta is basically becoming -1 at each step along this side itself. So Duran in the next step will be here, next step will be here, and then he'll also be running afterwards. So obviously the smaller border, it does not matter because by the time he reaches the larger border, larger boundary over here, the smaller boundary would have already been caught up by Duran. That's the whole point. Yeah. What is the case of -1? There is no case of -1. It's always possible for um Duran to catch Craig or whatever the names were. I explained that in the very start. You can rewatch the video. There's no -1 case for this question. Yeah. So let me just write down the logic a bit formally. So formally, given relative positions delta x and delta y, right? Um, until x dash moves have occurred, then what we can do is we can each move will change delta x delta y to delta x delta y minus 1, and after x dash moves, it will become delta x minus 1 delta y minus 1, right? So that's what, if this is if we choose to preserve the x dash coordinate. Now if we choose to preserve the y dash coordinate, that will mean until y dash moves have occurred, we're preserving the y dash coordinate now. Delta x delta y will become delta x minus 1 delta y, right? So after y dash moves, um, it will become delta x minus 1 delta y minus 1, right? Then he'll start catching up on him, right? So basically what we'll choose is basically, um, this is delta x plus x dash. This is how long he'll survive along this border. Delta y plus y dash along this border. So we'll take simply min of both of them. Okay, so there are many implementation for this. The way I implement is direct. So um, in my code, in my code, we basically have delta x is equal to, I've written it as dx. Okay, so I've written dx as delta x and dy as delta y. Okay, and x dash, which is basically, um, so if this is Duran and this is Craig, then I want x dash to be this much, right? This should be x dash. So that's, let's say his coordinate was x1, so this will be n minus x1, right? And if Duran came after Craig, so if their positions were swapped, if this is Craig and this is Duran, then this is the value of x dash, right? So this will be equal to x1, right? So value of x dash if x of Duran is less than x of Craig, then it's equal to n minus x of Craig. If x of Duran is greater than x of Craig, right? Then it's simply equal to x of Craig, right? And if x of Duran is equal to x of Craig, what happens in this case? Okay, so we need to think about this case where x dash is where they're both insiding, right? So let's say I have I have Duran over here, and I have Craig also over here, right? So now it makes no sense for me to go left and right, because anyways Duran will catch up, right? Anyways Duran will catch up. So it's always better for me to go towards this border, right? Because if I go left, Duran will go like this. So one up and one right, or one up and one left. If I go right, Duran will go one up and one right. So right now it is best to just go to the boundary. Then if we go left and right, it does not matter because he's going to catch up with us anyways, right? In that much time. So Craig might as well go over here and stay over here, and Duran will catch up to him. So in the case that x of Duran is equal to x of Craig, we can simply set x dash as 0. We don't want to go in along this boundary itself, right? So x dash. Similarly for y dash. Okay, similarly for y dash. And then our answer is min of delta x plus x dash, delta y plus y dash. Okay, so this is our answer. So yeah, I think it was a bit harder than normal B. I understand if people did not quite get it, but it was a bit intuitive. I saw some people who did not know any of this logic and they got it through pure intuition, which also works, right? If you play games like chess, this will be, like all this mathematical proof is not needed if you have good intuition, right? So this is the code. Code itself is simple. Delta x and delta y are simply difference between their coordinates. I'm setting, this is basically x dash. Okay, ddx is x dash for distance to boundary away from Duran, basically, or Craig's distance to boundary away from Duran. Similarly, this is in this is in the x direction, this is in the y direction, and we're taking max of these two cases and putting it as output. Okay, so that's it for this question. I know it could be a bit confusing, especially if you didn't solve it. So do rewatch this part, do go through the code, hope and go through the proof. Hope you understand it after that. Right? So yeah, that's problem B. Um, hope it was understandable. Should we move on to the next problem, guys, or are there any doubts? Along the way. Because I said a lot of things mathematically, like I said, x dash, delta x. Understand what x dash and delta x mean, right? Delta x is relative position, x dash is position from him to the boundary. If you write down some finite values, try and understand it. You can try and understand. What is the rating of C? C, I think, would be 1200, maybe. C seems like a 1200 to me. Anyways, let's move on to problem C now. Problem C. Okay. Yeah. Oh, one thing we forgot. Problem B, the time complexity. Obviously, it's a direct mathematical formula, so time complexity is big of 1. Right? Time complexity is big of 1. Okay. Let's move on to problem C now. Problem C, triple removal. Given an array, there's an operation called triple removal. When there are three identical elements, it removes all three. The cost is min of k minus j, comma j minus I. So what does that mean? It means that this is your array and we remove three elements. Then all these elements have to have the same value, right? So like 7, 7, 7, all of them have to be equal to 7, let's say. And then let's say two elements are like this, one is like this. So this is going to be I, j, k. Right? So this is going to be j minus I. It's going to be k minus j. Right? And whichever is the minimum, that is the cost of this operation. Right? Whichever is the minimum, that is the cost of this operation. Right? And once they are removed, there's a new array formed with them removed. Fine. We want to make array be empty using this operation. So we define total cost as the minimum sum of triple removal operations. If it's impossible to empty the array, cost is minus 1. Okay. So now we understood the question. We need to do the following. So we need to answer k independent queries. So we're given an initial array, and for each query, we should answer whether in the range from L to R, what is the cost? Okay, in the range from L to R, what is the cost? And we're also given that each element is 0 or 1. Okay, so they should have probably bolded this because important, each element is 0 or 1. And what is the cost between some range? So this is a query question, right? This is a query questions. I particularly am fond of these types of questions. So queries, answer queries, right? So that's what we need to do. And in each query, first of all, A is equal to some series of ones and zeros, right? Zeros and ones. Each query, answer the minimum cost, min cost, right? To empty, L comma R using triple removal, right? And what are our time complexities? So let's have a look. Time complexity n and q go up to 2 times 10 power 5, right? So n, q go up to 2 times 10 power 5 roughly. So that means our expected solution is big O of n plus q, or big O of like n log n plus q log n, something like this, right? Big O of q log n, something like this. We are expected that it should be at most n times some log factor. And that's going to be our solution, right? Expected time complexity, right? And obviously some query type of question. So we'll need some data structure, we'll need some prefix, some DP, something to help us out and figure out the answer. Yeah, sometimes they are. Also, Div 1 plus 2 is sponsored, right? Like this one is sponsored. So usually the sponsored ones tend to be better quality questions and more interesting mathematical questions rather than the normal ones. I've seen that before. So yeah, let's move on to the question now. So, okay. So first we need to figure out some basic facts for when a given array, right? When an array, let's not think about subarrays from L to R yet. We'll just figure out when an array from of zeros and ones, like what's its cost, right? What is its cost? Okay. So let's take any example array and try to figure it out. Okay. So let's say we're given an array like this 0, 0, 0, 1, 1, 0, 1, 0, 1, 0, 1, 1. Okay, so this is our array. And what will be the cost of this array? Well, we can choose any three elements which are equal, right? Since the only elements are zeros and ones, that means that either we pick a triplet of zeros or we pick a triplet of ones, correct? So one thing becomes very obvious, right? So obviously the count of zeros or the number of zeros should be divisible by 3, should be divisible by 3 because we're removing triplets, right? So should be divisible by 3, and the count of ones should be divisible by 3, right? Right? So these two things are very obvious observation, right? So mark this, that obviously the count of zeros must be divided by 3. Otherwise, if we keep removing triplets, how will it become empty, right? If it becomes empty, that means that it's divisible by 3. Okay. Now let's try to solve this example, right? We need to remove this with minimum cost. Well, if you observe, this triplet is right next to each other, right? Specifically, this 0, they are right next to each other. So what we can do is we can use um, this and this one over here, right? If we use this, and this one over here, why are we using this one far away instead of the near one? You'll see. So let's say if we use these two and this one over here, with the cost 1, we remove them, right? The cost is 1 because um, j minus I is equal to 1 itself here, right? The distance between these two is 1 itself. So in a cost equal to 1, we remove these, right? So we remove them. So let's say we deleted this and we deleted this one. Okay. Now in this new array, right? So in this new array, we'll just write the array. So there was a 1, 1, right? So now in this new array, we have something like this. Now again, we say that, oh, there are two 1, 1s together over here, right? So let's say we remove this one, right? And we took this one out, right? And now let's say we deleted these. So these two go, right? These two go, and this one will also go, right? And this is our new array form. So we have 0, 0, 1, right? And the cost so far is equal to 2, right? The cost so far is equal to 2. Now again, these two zeros are together, so their cost will be 1 if we remove this. So we remove this, and now there are these ones remaining, right? There are ones remaining, and we'll remove this also, right? So the total cost for this example was 4, right? The total cost for this example was 4. And in fact, we can get this general idea if you do some examples, right? If you do some examples, you get a general idea or general intuition that if in our array, in our array, there is a there is a 0, 0, together or 1 1 together. Okay, so that means they both have distance of 1. Then the answer is simply equal to number of triplets formed. Okay, number of triplets formed. Each triplet is being removed at a cost of 1. Okay, each triplet removed being removed at a cost of at a cost of 1. Okay, and why is this happening? Just observe. Okay, so let's try to take an array where there's some a bit harder. Okay, a bit harder array like 101 and then something like this, right? Here there's a 1 1 only at this position, and there's no 0 0, and the only thing which is satisfying is this 1 1, right? So now what we'll do is we'll take these two as 1 1, and then we'll take this, right? So when we take this, what happens is once we remove them, we get a 0 0 which is formed, right? These two become 0 0. So when we take these 0 0, we'll remove this 0. So what happens is basically we get a 1 1 which is formed, right? So basically we're able to remove all triplets at only a cost of 1, right? Able to remove all triplets at only a cost of 1, right? Because basically what we're ensuring is that when there is a 0 0 together, then we can remove it and form another 0 0 or another 1 1, right? And similarly, when we have a 1 1 together, we can form another 0 0. That's what's happening, right? So if the array had no other 0 0s or 1 1s, what if it was a perfectly alternating array? Okay, so exception, the only exceptions are perfectly alternating array. They don't have 0 0 and 1 1, right? Perfectly alternating array. Which arrays don't have 0 0 next to each other or 1 1 next to each other? Obviously, if they're alternating, right? So perfectly alternating array, right? So let's say we have a perfectly alternating array. Let's say 0 1 0 1 0 1 0 1 0 1 0 1 0 1 0 1, right? If you see the count of zeros are divisible by 3, the count of ones are divisible by 3. So this is valid, right? Count of zeros is 9, count of ones is 9. So now for this, we have no option but to try and choose a 0 0 which are farther apart. Okay, we have no option because there's no 0 0 next to each other. There's no 1 1 next to each other. But okay, we'll remove this 0, and this 0. Fine. So that will cost us 2. Why 2? Because distance here is 2. Distance here is 2. So we'll for a cost of 2, we'll remove it. Okay, cost of 2, we will remove it. So cost of 2, right? And what do we get? We get this, right? So the cost has increased by 2, right? But now as you can see, there's a 1 1, right? Now as you can see, there's a 1 1. So obviously the remaining will just be the number of triplets, right? We removed one triplet. How many triplets are remaining? So they are total 18 elements. 18 means 6 triplets, right? So 5 triplets are there, 5 triplets. And as you can see, this 1 1 can go with this 0. Sorry, this 1 1 can go with this 1, right? And then what will happen is basically we'll get this will go and then this will go. And then we got a 0 0 together, which will go with this 0, let's say. Then this 0 0 will get cut out and this 0 will get cut out. Then we got a new 1 1, right? And so on. So the whole array will be empty and the total cost will be equal to total number of triplets plus 1, right? Plus 1. So what did we learn? We learned the following major observation, right? Major observation for cost, right? We simplified the cost a lot. It is if array is perfectly alternating between 0 and 1, right? Between 0 and 1, then answer is equal to total number of triplets plus 1, else answer is equal to number of triplets, right? So this is what we have observed. right? So first we need to check if if we can form triplets at all. So it must be divisible by 3, right? Then next we need to check if it's perfectly alternating or not. So basically, coming back to the original question. Right now we solved only for a single array, right? So now back to the original question. Still much of the question is left, which is basically we need to test if um if given range L R is has divisible by 3, right? Has divisible by 3 of ones and zeros, number of ones and number of zeros is divisible by 3. And second, if it is alternating one zeros, if it is an alternating sequence or not, right? Alternating 0 1 sequence or not, right? Or the other way you can test it is to check if there is a 0 0 or a 1 1. Okay. So the other way you can check it is if, or is there a 0 0 or 1 1 as a subarray, right? Right. So this is what we need to test. Based on that, we will get our answer as triplets or triplets plus 1, right? Triplets or triplets plus 1. Basically, the length divided by 3 or length divided by 3 plus 1, right? So how do we do the first test? How do we do the first test, right? To do the first test, we simply need to, we can do prefix sum, right? Prefix sum. So if we sum the array, it will be the, if we take a prefix sum from range L to R, it will be the total number of ones, right? If you take the sum of this is equal to 3, which is equal to the number of ones, right? So number of ones, sum of subarray is equal to the sum like this. So that will simply be the number of ones. So we can check if it is divisible by 3 or not. Similarly, number of zeros will simply be length minus prefix, right? Sum from L to R of A of I, right? So this is number of zeros, right? So we need to check if this is divisible by 3 and this is divisible by 3, right? So this is to make sure that we can form enough triplets. Now, how do we check the alternating sequence? We can check that in two ways, right? How to check if it's alternating sequence? So I'll give you two strategies and I'll tell you which one I used, right? The first strategy is sets plus binary search slash lower bound, right? Lower bound. Or the second strategy is um, dynamic programming, right? Dynamic programming idea. Okay. So in the set strategy, I will just tell you, but I will not show you the code for this because I didn't do it. But I'll just tell you the idea. Okay. So we need to look for 0 0 or 1 1, right? So we can store the position each time we see 0 0 or 1 1. Store the position. Store the position of zeros and 1 1s in a set. Then in L and R, in L comma R, do lower bound, on set and check if it is present. Check if it is present. So this is our first strategy, and this will be log n per query, right? Log n per query. So q log n, and to make the set will be n log n, right? So let's write the time complexity. To make the set will be big O of n log n, and for query it will be log n, right? And in the dynamic programming idea, I'll show you how to solve it in big O of n plus q. And basically, we will have dp of I like this. dp of I is equal to length of longest alternating sequence. This is a standard question, I think. Length of longest alternating sequence ending at length I. And length of longest alternating sequence ending at length I. Then we must simply check. We simply check if r minus dp of r, right? R minus dp of r. If this is less than or equal to L, right? That means that I'm basically in the range R, you're at position R, and your longest um, alternating sequence was length 8, let's say, right? And from L to R is only 5, right? So that means the whole thing over here was alternating, right? That means till 8 it was alternating, right? So here it breaks, let's say. Here there's a 1, 1. So that means that um, your whole range is an alternating sequence, right? So this is your length of longest alternating sequence ending at your position R, right? So let's just start this, right? Now we just need to compute the DP table. We can check the DP table in big O of 1 itself. So each query can be answered in big O of 1, right? Query can be answered in big O of 1 once we have the DP table. Now how to do the DP? So DP was, what was our DP again? DP of I was longest alternating sequence ending at I, right? Sequence ending at I. So what we can say is DP of I is equal to DP of I minus 1 plus 1 if A of I is not equal to A of I minus 1, right? If A of I was 1, A of I minus 1 is 0, or it's 0 and 1 or the other way around, right? Then it's dp of I minus 1 plus 1, or it's simply equal to 1, right? Because in that case, there is no alternating sequence, right? So this is a very simple dp. In fact, it's so obvious that even if you don't know dp, I think if you're trying to look for it, you would come up with this, right? So this is our dp to check if longest alternating sequence ending at I, right? So let's have a look at the implementation now. Okay. So we take in n and q, number of elements, number of queries, input all the elements. We are creating a prefix sum array, y, to count the number of ones, right? So basic prefix sum array. Now we're creating a DP array, the same DP array. Each has a default value of 1. If a of I minus 1 is not equal to a of I, then we can add DP of I minus 1, right? So we can extend the alternating sequence. Now for each query, we take in L and R. First, we're checking if it's divisible by 3 or not, right? So if the sum, prefix sum, is divisible by 3, and also instead of checking length minus sum, we can just directly check length, right? So instead of length minus sum, since sum is divisible by 3, we need to check if length is also divisible by 3, right? If it's not, then it's minus 1 because we cannot even form that many triplets. Otherwise, our answer is simply number of triplets, which is length by 3. If L is greater than R minus dp of R, right, then the answer increases because then it is an alternating sequence. Otherwise, the answer remains the same. It's not an alternating sequence, so it's simply length by 3. Right, so that's the solution to this problem. So final time complexity is big O of n plus q. Right, prefix sum and dp both are big O of n. Finding the answer also big O of n with them. Show the general way. The other way is simply you need to find 0 zeros and 1 ones, right? So just use the set. Each position of 0 0, you can just store in a set, and you can check if that lower bound of that 0 0 position or 1 1 position, if that is in your range L and R. So that will be n log n q log n factor for using set. Yeah, so I think there are both these ways. There might be other ways as well. Obviously, if you want to know the DP solution, I can't explain DP right now from first principles, right? To understand the DP solution, you'll need to have practiced some DP. But yeah, it's a pretty basic DP idea over here. Not even hard, one-dimensional DP. Okay, so we'll take a break of 2 minutes and then we'll move on to problem D. If there are any doubts, please just put it in the chat. Okay, problem D. We'll just quickly take a break of 2 minutes and I'll be back. Yes, Sath, your answer for problem B is correct. Macton. Yeah, Dom will probably be Elgin. Yeah. If you're doing from scratch, yeah, 6 months does seem reasonable. So good answer, Raghav. It should take around 6 months if you're doing from scratch, depending on how much time you put into it. Anyways, so let's move on to problem D now. Okay. So again, we have a query type of question which we need to, figure out how the solution works in do queries. So I guess they like query questions a lot this time. So anyways, for an array B, consider the following game. So there's an array of some numbers, which all the numbers are greater than equal to 2. Okay, so pay attention, all the numbers are greater than equal to 2. And then the players take turns. In each turn, they take some x and replace it by x divided by 2 floor. Okay, Bobby's turn, he takes it and replaces it x by 2 floor. And on Reckel's turn, he um he takes some element and replaces it with x plus 1. Okay, so each of the picking elements which are greater than equal to 2 itself. Okay, so replace with x plus 1, and then the game ends once all the elements are equal to 1. Right, so if you observe, um if you keep doing x by 2, it will become 1 eventually, right? So once all the elements are equal to 1, the game will end. Score is the number of moves which Bobby makes. Bobby wants to minimize the score. Reckles wants to maximize the score. Value is the score when you play optimally. Now you're given an array and you have to answer queries as usual. You have to answer queries given in a range L to R, and they play optimally. What will be the value? Right? So again, queries goes up to 2 times 10 power 5. Each element is up to 10 power 9, right? And again, we need to find some n log n plus q log n or n plus q solution, right? So another data structure type of problem. So expected big of n log n plus q log n, or etc. These kinds of things are expected, right? Anyways, so yeah. So first, obviously, instead of thinking about the subarrays, we'll try to analyze the queries themselves, right? How is system testing going? Okay, so unfortunately, I was not able to solve E during the contest. Anyways, makes sense. Anyways, so let's get into it. Okay, so we'll try to break down the queries which are given. Okay, so we'll try to break down the operations which are given, right? So what does Poby's operation do, right? Because obviously whatever form they've given it, that's not going to be the correct form to understand the question, right? It's a D question. So Poby's operation takes some value B greater than equal to 2, and it does Bi divided by 2. And Reckel's operation, what it does is it takes some Bi greater than equal to 2 and converts it to Bi plus 1, right? So now clearly Poby's operation is the important one, since the number of operations he takes is the score, right? And his goal is to make it equal to 1. Goal is make make everything equal to 1, right? Equal to 1. Now one thing should be obvious, that as soon as some value, let's say it was like 3, and let's say Poby did an operation, he divided by 2 and floored, so it becomes 1, right? So now Reckel cannot touch this anymore. Once it has become a 1, obviously Reckel cannot touch it anymore, right? Reckel can only touch values greater than equal to 2. So once it has become a 1, it's going to stay a 1, right? So once it has become a 1, it's going to stay a 1. Okay. So now how do we think about this operation in a clever way, right? Here we see division and flooring, right? And again, all the numbers go up to 10th power 9. And here we see addition. So we get this idea that we'll think about these numbers as binary numbers. Okay, as binary numbers. Or basically think of their bits. Think of their bits. Or think of the bits of the numbers. Okay. So let's just take a simple example, which let's say they have given. Um, yeah, actually their examples are too short, so let's just make one of our own, right? Um, let's make an array 5, 4, 2, 3, 6, maybe something like this. Okay. So now each number, instead of seeing them as numbers, we'll try to see them as bits, right? Because that's the thing which is making sense right now. So 5 will be seen as 101, 4 will be seen as 100, 2 will be seen as 10, 3 will be seen as 11, 6 will be seen as 110, right? Now we'll try to interpret Pobbe's and Reckel's operations in terms of bits. What does Pobbe's operation do? It chops off the last bit, right? It does a right shift by 1. That's what division by 2 in bits looks like, right? So it basically is chopping off the right bit, right? So if Pobbe chooses some number and does it, it can like chop off this bit, right? Or if he does it to 3, it chops off this bit and becomes equal to 1, right? Obviously, if you chop off enough bits, it will become equal to 1, right? So Pobbe's operation is like chop, chop, and then it becomes equal to 1, right? So if there's a longer number with more bits, then it become like chop, 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 and it will become equal to 1, right? What does Reckel's number do? Reckel's number adds a 1. So for example, Reckel can choose this number 4 and make it into 5. So you can add a 1 over here, right? Then Pobbe can maybe chop it off later. So Pobbe just wants to make everything equal to 1, and Reckel wants to slow him down, right? So let's take an example. Um, yeah. So one thing should become obvious is that Pobbe is going to be basically limited by the numbers bit width or bit length, right? Which basically means this length, which is like 3, this length is 3, this length is 2, right? So basically, in the best case scenario, Reckel does not exist, right? Best case scenario, Reckel does not exist. What Pobbe is trying to do is he's trying to chop off this number. So the time it will take him or the number of steps it will take him will be simply the bit length minus 1. Okay. So here the bit length is 3. So to do one chop, it's 1. And to do another chop, it's another one. So two chops he's taking, right? So bit length minus 1. So bit length can be defined in many ways. So you can do it as um, log base 2 of n, right? This value is the bit length, right? Largest power of 2. Or we can write bit length as so there's a predefined way in C++, which is basically just we find the highest bit and minus that with the total number of bits. So you can do this minus built-in Z, which is count leading zeros, right? So this will give us the bit length in C++ quickly, right? So basically, in the ideal scenario, in the ideal scenario for Pobbe, the answer is going to be simply bit length, sum of bit lengths of all the numbers, right? Sum of bit length minus 1. So I'll just call it BL. So sum of for all the numbers from L to R, whichever the query is. So all the numbers from L to R, the sum of bit length minus 1. This is going to be his answer. This is the minimum he needs to chop definitely. Right, this is the minimum number of times he's doing the division by 2 step. Okay. So now this is the ideal scenario. But now Reckel is there to increase the numbers a little bit, right? So let's think about it. So here we know that Poby has the first step, but let's just think about it from a different scenario. Think like Reckel had the first step. Okay, think Reckel had the first step. Okay, and we'll try to do the game for different numbers. We'll try to figure out some pattern. Okay, so think like Reckel had the first step. Then um, let's say we're given a number like, for example, 3. Okay, for example, 3. Now, what happens if Reckel adds 1 to 3? Basically, he's going to flip these bits, right? So these bits get flipped, and this one becomes a 1, right? So 3 plus 1 equals 4, right? 3 plus 1 equals 4. So basically, you would write it like this in binary. So 3 plus 1, right, is equal to 4, right? So essentially, what this does in binary notation is, like if you have a series of ones and you add a 1 at the end, then whatever the next 0 is, this is the next 0, right? This becomes a 1, this will become a 1, and all of these will get become zeros, right? Because it's going to carry, the 0 will carry, right? So this is what happens when you add a 1 to a series of add a 1 to a series of ones, right? In a binary representation. Okay, so this is what addition basically means in binary, if you know adders and how they work and stuff like that, right? So what Reckel is trying to do is that whenever some number ends with this 1 1, right, he can add a 1 and he can make a new bit itself, right? So for example, um, if you have the number 3, right? So if you have the number 3, which is like this, and you add a 1, it becomes 4, and its bit length will increase, right? Its bit length increases, right? Now instead of chopping 1, like this guy has to chop 2 now. Right? Instead of chopping 1, we have to chop 2 now. Right? For 3, we just had to chop 1, but now we have to chop 2. 2. So Reckel will try to add 1 to increase the bit length, to increase the bit length of the numbers. Okay. So we need to now figure out when he'll be able to successfully increase the bit length. When can Poby come before him? Okay. So let's take an example array which is just threes. Okay, there's a bunch of threes. Fine. So now in this bunch of threes, so the numbers will look like this in binary, right? 0 1 1 0 1 1 0 1 1 0 1 1, right? So what will Poby do? Poby has the first move. He will remove this bit and it will become equal to 1, right? So he chops this off successfully, and this is equal to 1 now. Now these others are remaining to 3. So Reckel will add 1 over here, right? Reckel will add 1. So this becomes a 4, right? This becomes a 4. Now again, Poby can chop this one off to protect it from Reckel. So this one becomes 1, right? Now Reckel will add again 1 over here. So this will become 4, right? This will become 4. And um, Poby will chop this one off. So this will become 1, right? So the number of chops it took here was chops equals 1. Here the number of chops it took was again 1. Sorry, here the number of chops, it's not equal to 1 yet. So here also chops is equal to 1. And here also chops is equal to 1. Right, so number of moves by Poby. That's basically what we need to minimize. Now what will Reckel? Reckel is going to try increase this by 1 again, right? But now Poby will just directly follow his moves and chop it off, right? Again, he'll try to increase this by 1, but it will be chopped off. And so the number of chops taken here will be 2, right? Similarly, the number of chops taken here will be 2, right? So for some of them, it is bit length minus 1. And for the others, it is bit length minus, it is equal to exactly the bit length, okay? So I can hope you understand. In some of them, Reckel was able to solve it, was able to get to it and add 1 and increase the bit length. In the others, he was not able to increase the bit length, right? Now, what if the number is something like um, 4? Okay, what if the number is like 4? Now, there is no point in Reckel doing anything because as soon as he increases 1 over here, it will get chopped off immediately. In the next move itself, Kobe might as well chop him off, right? So, there's no point in increasing 1, no point in increasing 1 for numbers which are like powers of 2, right? By Reckel. Right, Reckel is the one who can add 1 uh, on these numbers which are like powers of 2. Okay, on these numbers which are powers of 2. Okay, so yeah, we're, we just need to make a few more observations and then we'll be done with this question. So let's try some more different types of numbers, right? So basically at this stage, you should try different types of numbers and see what happens. Try the strategy. So if we have a number something like this, okay, so let me just give you an example of 3 different types of numbers. So one number is like this, is the perfect power of 2. Another number is like this, and it ends with a 1, right? And another number is like this, which has some 1 somewhere in between. Okay. So basically, when you try a bunch of examples, so obviously trying examples in front of you right now, trying 10, 20 examples will be a waste of time. But yeah, please note that even in during the contest, I also had to try almost 10, 20 examples before I like got to these conclusions. So yeah, but it turns out that these are the 3 major cases. Okay, one is perfect power of 2, one is perfect power of 2 plus 1 at the end, and the other one is perfect power of 2 and 1 is somewhere in the middle. Okay, and we'll see why. Okay, so if it's just a perfect power of 2, even if Reckel increases 1 over here, Kobe can just chop it off, right? And then it will become like this again, another perfect power of 2. Again, if Reckel increases 1, Kobe will just chop it off, and then it will become another perfect power of 2. So for perfect powers of 2, the answer will always be bit length minus 1. Okay, so for perfect power of 2, score required will always be bit length minus 1. Okay, let's call it bit length minus 1. Okay, now what about this kind of a number where it's a perfect power of 2 plus 1? Okay, there's a 1 at the end, right? And what happens over here? So basically, in such a case, if Poby gets to it first, if Poby gets to it first, he will just chop this off, right? He's going to chop this off, and then it will become a perfect power of 2, right? If he gets to it first, he will chop it off, and it will become a perfect power of 2. So he has no issues. But if Reckel gets to it first, he will add 1, right? He will add 1, and then this will become 1, 0. Now, if Poby chops this off, again he will add 1, and it will become 1, 0. Now, if Poby chops this also off, again he can add 1, he can keep continuing this, right? And Poby will chop this off, he will add another one. Poby will chop this off, he'll add another one. Poby is going to chop this off, and it'll become like this, right? And let's say Poby chops this much, right? And then it reaches up to this value, which is 3 basically. And then again he'll add another one. So it'll become 0, 0, 1, right? As you can see, it becomes 0, 0, 1, which is 4. And then he chops this, chops this. So basically, one extra bit length was achieved. One extra bit length was achieved was achieved by Reckel. Okay, by Reckel in this case. So when it's a perfect power of 2 plus 1, then what happens is it depends on who gets to it first, who makes the first move on it. If it is Poby, then he can maintain his score. But if it is Reckel, he will increase the score by 1. Okay, so if Poby does first, right, then the answer for this case will be score contribution will be simply bit length minus 1. Otherwise, score will be equal to bit length. Okay, if Reckel gives first. Otherwise, Reckel attacks it first, then he can increase the score. Okay, so this is for this one. Okay, now what about the third case? There is some 1 in the middle, or there are a bunch of ones, right? There are a bunch of ones like this, or there is a 1 like this, and a bunch of zeros and a 1 in the end. Anything like that. So I'm just going to show that even if there's some 1 in the middle, the answer will always be bit length, or Reckel will be successful, and I'll show you why. Okay, so at some stage, Poby will have to start cutting this number, right? Poby will have to start cutting this number. He will cut off the last bit. Okay, then he'll cut off this bit. Okay, then he'll cut off this bit. Okay, but as soon as he comes here, right? As soon as he comes here, and he'll come here after cutting some bit off, Reckel will just attack this number. He'll add a 1. Okay, he'll attack this number. He'll add a 1. Now The one has propagated to the next step. The one has propagated like this, right? Now Poby is forced to cut off this zero. As soon as he cuts off this zero, Rekkel is going to add another one, and then this one will propagate like this. Now Poby is forced to cut this off, right? Later he'll cut this off because Poby obviously wants to cut everything to one, right? And then obviously before Rekkel will add another one, right? Rekkel will add another one. It becomes like this. When Poby cuts this off, Rekkel will add another one, and it'll become like this. And then finally, if he adds another one, it'll become 100, right? It'll become 100. So no matter what Poby does, he will never avoid this fate. No matter what Poby does. For a number such as this, he will never be able to avoid this fate, right? Because the one is there somewhere in the zero. He cannot chop off this one in the first step itself. The one is there somewhere in the middle, and that's going to act as a carry basically. This is going to act as a carry. This is acting as a carry. If you know how binary carrying is working, right? So acting as a carry for Rekul, right? Because this one is at the corner, so he's chopping it off early itself. But if it's in the middle, he won't be able to chop it off, and Rekul will get his carry, and he'll be able to increase the bit length. So in this case, the score will simply be bit length, no matter what Poby does, right? Rekul will always be able to make the score equal to bit length. Okay. So basically, we saw there are three types of numbers, right? Is type one is power of two, right? For this always bit length minus one. Um, type two is power of two plus one, right? Power of two plus one. And for this, it depends on who gets it first. And type three is any other number. And for this, the score will always be bit length. Okay. So for power of two plus one, that's the only thing we care about, right? So now one more thing we know, right? One more thing we know. Poby moves first. Poby moves first. So let's say there are n numbers. There are n numbers, n numbers of the form power of 2 plus 1, right? So let's say we have 3, which is power of 2 plus 1, 3, another 3, and another power of 2 plus 1 we could have is 5 and 9, 9, 5, right? So let's say there's an array, a bunch of these numbers, right? So Poby will save one of them. Basically, he'll make this equal to bit length minus 1. And then Rekkel will also get one of them. So he'll make this equal to bit length. Then Poby will get this one to bit length minus 1. Rekkel will get this one as bit length. Poby will get this one, right? Rekkel will get this one. And basically n by 2 are being saved or protected by Poby. N by 2 are getting attacked by Rekkel, right? And since Poby is first, it will be basically Rekkel is getting floor of n by 2 of them, right? Rekkel is getting floor of n by 2 of them, right? So Rekkel successfully increases the bit length. So Rekkel's color is yellow here, so I'll write in Rekkel. Rekkel successfully increases bit length, increases the bit length for n by 2 of the power of 2 plus 1 numbers. Okay. All the other numbers, no matter what happens, the score is fixed. This will always be BL minus 1, and this will always be BL, right? Only in this it matters. So now we can think about how to answer the queries, and it's pretty simple now, right? How to answer queries. Answer queries. Obviously, for each number, we'll have bit length and bit length minus 1 for normal numbers stored away, right? So for each power of 2n and power of 2n minus 1, right? Sorry, plus 1, store bit length minus 1, okay? And for others, for others, store bit length, right? Take prefix sum of this, take prefix sum, right? So then our answer can simply be prefix of r minus prefix of l, right? Prefix of l minus 1, right? But there's also the ones which are power of 2n plus 1, right? So each time we have a power of 2n plus 1, we'll store those also, right? We can store them in a separate array. Mark these in a separate array, right? So then for um, each query, count of power of 2n plus 1 numbers, let this be equal to count, right? So answer increases by count by 2, right? So those are the ones which Rectal increases the bit length. So for all of them, we have to increase by count by 2. And then we can print the answer for each query, right? So the pre-processing is basically just finding bit length and prefix sums. So we can find bit length in big O of 1 if you use the built-in function. If you use the built-in function 64 minus built-in count leading zeros, right? Then we can find the bit length in big O of 1. So the time complexity for this, we can reduce it to big O of n. And taking prefix sum also big O of n. To keep this count also, we'll take prefix sum in big O of n. Now for each answer, we need to subtract prefix sums. We need to find the count also using prefix sums itself. So count of, let's say, r minus count of l minus 1, basically, right? This is O of 1. So each query in O of 1. Okay, each query in O of 1, right? So the total time complexity for pre-processing is big O of n, and for answering the queries is big O of q, right? So this is the total time complexity of our idea. Cool. So what could be, yeah, Tom became LGM. What could be the reason for what? Rating of the problem. Okay, rating of the problem, maybe this one is decently hard. Actually, I'm not very sure. The idea took me some time, but um, I would say it could be between 1600 to 1900, somewhere. I'm not sure. It took me like half an hour-ish, right? So somewhere in this range should be the rating. So let's have a look at the code now. Okay. Yeah. So this is the bit length function, just 64 minus built-in CLZ. So that was just template. Input number of elements, number of queries. Here we're storing in n plus 1, right? Because we want to do prefix minus, like prefix of r minus prefix of l minus 1. That's why I'm storing in one based indexing. Okay, that's all. Just make a note of that in the code. It's one based indexing. Okay. Now, BLs is basic lengths, right? So BL is equal to prefix sum of bit lengths. BLs is prefix sum of bit lengths. And what is fight? Fight is basically equal to the count of 2n plus 1 cases, right? And why did I write it as fight? Basically, that's when these two are fighting, right? That's when Reckel and Bobby are fighting for those numbers, because those are the only numbers where we can change the answer somehow. So yeah, how many numbers they're fighting on? That's the fight array. Okay. So then I will take input of a of I. I will store the bit length in my array, bit length array. So bit length minus 1. Now this is how you check perfect power of 2. Okay, this is how you check perfect power of 2. Perfect power of 2. So it's a simple bit trick. I think if you know bit tricks, you'll be able to do, right? X and x minus 1. If this is equal to 0, then it's a perfect power of 2, else it is not equal to perfect power of 2. So if this is non-zero, it's not a perfect power of 2. And I'm checking if it is power of 2 plus 1. Okay, if it is power of 2 plus 1, right? And for that, I'm simply checking again the same strategy, right? If it is not a power of 2 plus 1, so not a power of 2 plus 1, and it's not a power of 2 also, then it is definitely increasing the bit length, right? So I just do bit length plus plus. Otherwise, it's of this form. It's a number which is 10000 and followed by a 1, right? So it's a power of 2 plus 1 form. So I mentioned that they can fight at this position, so I increase the fight variable over here. Okay. So these two will become prefix sums because we need to answer queries, right? So these two will become prefix sums. So we prefix sum them. Now we can answer the queries. We take in L and R. The answer is simply L R minus L prefix sum. And then this is the number of times which are 2n plus 1 form, right? So the number of cases where they're fighting. We increase the answer by f by 2 and then we print the answer. So yeah, that's about it for this question. It's just a bunch of observations that which numbers matter. 2 power n numbers are always dominated by Poby. Other numbers are dominated by Haeckel. In the numbers which are 2 power n plus 1, those they are fighting, right? So that's all we need to observe. And the queries can be answered in let me take you. Yeah, I guess so. Let's just check C list, right? Maybe C list has the problems already. Um, okay. Are the ratings updated? Let's go. We have a new legendary. We have the first legendary grandmaster from India. That's so cool. All right, then, everyone. I think it's pretty late now, so we'll be ending the session. Um, Good night, everyone. Yeah, yeah. It's cause for celebration, I guess. Good night, everyone. Hope you learned something. If you didn't get it, do rewatch those sections, go through the code, try some test cases by hand. Do upsolve the problems, right? Don't just watch the PCD, go upsolve the problems and go make a good coding culture in our country, right? All right. Bye bye.